All right, so we are going to look at linear algebra. This unit is going to focus on matrices, and you've done algebra of lines before, y equals mx plus b. We're going to look at that a little bit further. There's some applications in engineering and physics and a lot of computer science stuff. But to start off, we're going to review our systems of equations. One of the things that we're going to do in this unit is learn how we can use matrices to solve systems of equations. So here we've got a linear equation, y equals mx plus b, or you could have it in its standard form, ax plus by plus c equals 0. And a system of linear equations is when you have two lines. And those two lines, they might be parallel, they might intersect at one point. And way back in grade 10, you learned a bunch of techniques to figure out if they intersected at a certain point. So you could have a whole bunch of linear equations, or you could have two of them. And we learned that in order to solve a set of linear equations, you need to have two of them. If you have two unknowns, so x and y are the things that I don't know, and I have two equations, then I can find out a solution for this. Either those two lines cross at one point, and that point where they cross is the solution, or it could be that those two lines are parallel and they never cross, and then when you try to solve it, you'll get something that doesn't make sense because there are no solutions. Or these two lines are exactly the same line, in which case you're going to get an infinite amount of solutions. Do you remember some of the techniques that you used for solving this? There were sort of two main techniques, but maybe you've learned a third or a fourth one. Substitution. That was one technique. So if we were using the substitution technique, the goal is to get one variable by itself. Looking at those two equations, the fact that there's no equal sign, did I fix that on yours? No. All right, let's switch that in there. That is supposed to be an equal sign. Otherwise, this made no sense whatsoever because it wasn't two equations. Substitution. And then looking at both of those equations, is there a variable that you see would be the easiest to get by itself? X in which equation? Top one. So I'm going to call this equation A and this equation B so we can talk about them. You're right. In equation A, it's easiest to get x by itself. I can rearrange equation A by subtracting 4y on both sides to get x equals 6 minus 4y. The substitution technique says then go to your other equation. So now we're going to go to equation B, and wherever there is an x, I'm going to write 6 minus 4y instead. So it was 2x minus 3y. Now I'm going to write 2, and instead of x, I'm going to substitute in 6 minus 4y. And what that does is that it changes an equation with two things that we don't know to an equation with just one variable. And then you can use all of your techniques for solving equations, multiply that 2 through, combine your like terms. I'm going to get 12 minus 11y equals 1. Subtract 12 on both sides. Divide by negative 11. And we find out that y would have to be 1. Once you've solved for one variable, now you can take that value, y is equal to 1, go back to either equation A or B, and plug in 1 for y. So if I went back to equation A, it was x plus 4y, but now I can plug in 1 for y because I know that's the solution. And it was equal to 6. subtract 4 on both sides, and I get x is equal to 2. If you want to make sure that you haven't made any mistakes in solving this, you can go back to equations A and B, plug in 1 for y and 2 for x, and check. Does equation A add up to 6? When x is 2 and y is 1? Yes, it does. Does equation B equal 1? When x is 2 and y is 1, 4 minus 3 is 1. So we can check to see that both of those work. That's method number 1, substitution. Do you remember a second method? Elimination. So we'll do number 2 here. Elimination. So the elimination technique said if you can stack things on top of each other, your two equations, so that your x's line up, your numbers line up, your y variables line up, and they're already lined up here. My x's are above each other in equation A and B, and y's are above each other in A and B, and so are the numbers. Then if we can get a leading coefficient of one equation to be the same but opposite signs of the other equation, then it's really easy to solve this. So another thing that you're going to have to do, so our goal is to have our x's be -2 and 2, or our y's to be, say, 12 and -12. And again, you could choose which variable you want to eliminate, but often there's an easier one. So in this case, when you look at x and y, and if you wanted the coefficients to be the same, and you can get the coefficients to be the same by multiplying an equation by a number, is it easier to get the x's to be the same coefficient or the y's? The x's. Because I can take equation A and I can multiply it by -2. If I do that, my new equation A would be -2x minus 8y equals -12. If I rewrote my equation B right underneath, my equation B is still 2x minus 3y equals 1. So we've succeeded right here with our x's in having the same coefficient, and I like to have one positive and one negative. If you wanted to do the same thing with your y's, you would have to multiply equation A by 3 and equation B by 4. You'd have to do an extra multiplication. But then they would both have 12s as coefficients, and one would be positive and one would be negative. Once they're the same, except for a different sign, we can add the equations together. And when we add the equations together, our x's get eliminated. That's why it's called elimination. -8 plus -3 gives us -11y. -12 plus 1 gives us -11. I always like to add, so my goal is always to get the coefficients to be the same, but one negative, one positive, because I find I make less mistakes and students make less mistakes when they're adding rather than subtracting. Some people, you could make them exactly the same and subtract the two equations, and that will work as well, but just people tend to make a few more mistakes when they're subtracting than adding. So as a rule of thumb, I recommend adding. Anyways, now you would divide both sides by -11, you get y equals 1. And then to solve for x, exactly the same as we did last time, plug y equals 1 into equation A or B, and you'll get x equals 2 again. So it's exactly the same as before. So if we were to graph both of those lines, if we would change them to y equals mx plus b, we would get two lines, and those two lines would intersect at the point 2, 1. Just a quick look at them. One line looks like it's going to have a positive slope. The other line is going to have a negative slope. So we can imagine one line going like this, the other line going like that, and they're intersecting at the point 2, 1. So when we're solving that system of linear equations, we're looking for that point of intersection. But it's not always that they have a point of intersection. When they do, we call it an independent system. It has one solution. That happens when you have different slopes. And if you have different slopes, well, most often you'll have different y-intercepts. There is the possibility that they actually cross at the y-intercept and would have the same y-intercept. But for the most part, they're going to have different slopes. That's the key thing. As soon as you have two lines that have different slopes, they will intersect somewhere. If you have the same slope and the same y-intercept, that's going to be the exact same line. Sometimes those lines are disguised. Like I could have y equals 3x minus 5 written this way, and I could write this same equation as 0 equals 3x minus y minus 5. I just moved the y over. But if you were asked, can you find the intersection between these two lines, they might not appear to be the same at this moment. I could make them look even more different by multiplying this one by 2. And then it does look quite different. But those are still the same two lines. Because if you would rearrange this bottom one back to y equals mx plus b, you would get 3x minus 5. So they're exact same line, and you would get an infinite amount of solutions because the two lines would be on top of each other. And no matter what value you put in for x and y, as long as they're on one line, they'll be on the other line as well. And finally, there's the possibility that you have no solution. So in other words, you have two lines with the same slope but different y-intercepts. In other words, they're parallel, and those two parallel lines will never intersect, and so you'll have no solution. What we're going to do is, in the past, you've done mainly equations in 2 dimensions. We'll also do lines in 3 dimensions and look at trying to solve a system of equations with 3 unknowns and 3 equations. And of course, the other method to solve is by graphing it and just finding the point of intersection. Maybe. So here's the first one. Solve it by one of the methods. I'll put up the answer in a second. Okay, so something weird happens in this one. Again, I'll call this equation A, and this one equation B. For those of you that were using elimination, when you look like probably you multiplied the first equation by 2, and when you eliminated, you set up your line, you set up your equations A and B, and you got this. Okay? So you multiplied equation A by 2, which gave you 2x minus 4y equals negative 2, and you had negative 2x plus 4y equals positive 2, and when you added them up, everything got to be zeros. For those of you that use substitution, after you substituted, your y's went away, and your equation became 2 equals 2. Common fact, little well known, that 2 is equal to 2. And you wonder what to do with that. So you feel a little bit of a loss because you got something that ended up being sort of nothing. Now, what you got was something that was always true. 0 equals 0 is always true. 2 equals 2 is always true. If you have 2 equals 0 and you really want 0 to equal 0, you could subtract 2 on both sides. And you'll find out that 0 is equal to 0. And what we have here is something that's always true, and if it's always true, it should make you think that these are the same line. In which case, these are, in fact, if I take equation A and I rearrange it to y equals mx plus b, I'm going to get y equals 1/2 x plus 1/2. And equation B, if I rearrange it, I'll originally get y equals 2 over 4x plus 2 over 4. And I hope you can see that that simplifies to be exactly the same thing. So in a question like this, when you're solving it and you get something that's always true, you could take the time to rearrange it to y equals mx plus b to show that these are the same lines and end with a statement. So there are an infinite amount of solutions. So the weird things that are going to happen are when there are an infinite amount of solutions and when there are no solutions. When you have an infinite amount of solutions, whether you use substitution or elimination, you'll get what we got here, something that's always true. 0 is equal to 0, 2 is equal to 2. Okay? If you have something that has no solutions, and you use substitution or elimination, something similar will happen, in which case your x's and your y's will all cancel out, but you'll get a statement that is never true, like 0 is equal to 5, or 3 is equal to 7. So if you get something that is never true, then you know that you have a no solution one. So that's something to look for. Have you ever seen the proof that 0 is equal to 1? Well, we may as well get off topic a little bit. I'm going to prove to you through some mathematical magic that like 1 is equal to 2 or 0 is equal to 1. Okay, we're going to start off by saying let A equal to B. Two numbers, A is equal to B. So if I take this equation, and let's see, what should I do here? I'm going to, let's see. I'm trying to remember. All right, we'll come back to that. And want to here find a value of k so that this has no solution. Well, if it has no solution, what do we need? No solution things had the same slope but different y-intercepts. So if we arrange both of these to y equals mx plus b, again, I'll call this equation A and this equation B. For equation A, if I rearrange this, I'm going to get ky equals negative x plus 2, dividing everything by k. We get our equation to be negative 1 over kx plus 2 over k. For equation B, rearranging this, we're just going to get negative kx plus 4. So if we need this to have same slope, different y-intercepts, then the slope in equation A and the slope in equation B must be the same. So in that case, our negative 1 over k has to equal negative k. How would you solve this equation? Because this is my slope. If I highlight the slopes of my two equations, this is my slope of equation A, this is my slope of equation B, and if I need them to be the same, this is what it would look like. So I have a rational equation here. If you want to get rid of the fractions, you can multiply both sides by k. That'll give you negative 1 equals negative k squared, or k squared is equal to 1. Solving for k, k could be plus or negative 1 when you square root that. And you might have been able to see that just by observation, that 1 would have worked. But it's good to solve it because it might make you realize, oh, when I square root both sides, it could be plus or negative 1. Now we have to make sure that with both of those values, we get different y-intercepts. Can you see that the y-intercept is right there on both equations? I should probably change this equation. Be more fascinating if this was plus 4, because then only one of them would work. But in this case, can you see when you plug in 1 for k, the y-intercepts are different? When you plug in negative 1 for k, the y-intercepts are different. So both k equals negative 1 and positive 1 both work. But can you see if I would have changed the original equation to be a 4 here, which would make this a 4 there, then only negative 1 would work. Only negative 1 would get the slopes to be the same and still have a different y-intercept. All right. Yeah, I'm sorry about the spacing. So you might want to take out a scrap piece of paper. I can hand out some scrap paper. I'd like you to try this one with fractions. Different ways to go about this. In the end, the answers are x equals 7 and y equals 1. One thing that I did in this situation is I decided to get rid of my fractions because I knew they would cause me some problems. So if I multiplied equation A here, everything in equation A by 6, that's going to get rid of my fractions on the bottom. And that's going to change my equation A from that thing with fractions to 3x plus 2y equals 23. That's much easier to work with. In fact, when I stack my two equations, equation A and equation B, on top of each other, I already noticed that my y variables have the same coefficient but opposite signs. So when I add them together, my y's cancel out. Found y first, that's fine. So in this case, then 4x is 28, and solving for that. Ready? All right. Yeah, I remembered what I needed to do first. Okay. Now I'm gonna make some money. Let A equal B. Okay? So we're gonna start with that. That's our A is equal to B. Now if we would multiply the same thing on both sides, they're still equal, right? So if I multiply both sides by A, this side will become A squared. This side will be A times B. If I add or subtract things on the same side, they're still equal, right? So if I subtract B squared on this side, I could subtract B squared on this side. If you factor something, it doesn't change if it's equal or not. So if I factor this side, I get A plus B, A minus B, because it's the difference of squares. If I factor this side, I can factor out a common factor of B, and then get B times A minus B. If you divide something on both sides, they stay equal. So I've got A plus B on this side and B on this side. Now what did we start with? A was equal to B, right? So we've been learning about substitution. Wherever there's an A, I can put a B. Wherever there's a B, I can put an A. So I'm going to substitute in here, instead of A, since they're equal, I'm going to write B. So I get B plus B equals B, which means that 2B is equal to B. And again, if you divide both sides, you get the well-known fact that 2 is equal to 1. So you can go to your bank, give them $2 and say, no, wait a minute, that's the wrong way to do it. Go to the bank, you give them $1 and say, I'll take 2 back because they're equal. And then just keep doing that over and over again. If you want to use this fact, you can use this fact to subtract 1 on both sides to get 1 is equal to 0. And then if you multiply both sides by $1 million, you get 1 million equals to 0, and then that's more efficient for going to the bank. You say, give me $1 million, I'll give you 0 back. Since they're equal, that should be fine.
Does that mean
Infinity equals 0 if you would like to go that amount, that quick, right? But then you have to talk to someone high up in the bank, right? I've been trying the $4 equals 1 or $4 equals 0 since it doesn't cause as much mayhem as early on.